Έχουμε την χαρά να μας παρουσιάζει ο Σιμών, ο Dr Szymon ένα ενδιαφέρον θέμα σχετικά με τη χρήση των FRPs, δηλαδή των ενοπλισμένων πολυμερών, ως εσωτερικός οπλισμός διάτμισης σε στοιχεία οπλισμένου σκυροδέματος. Πολύ λίγα λόγια για τον Σιμών, αν και θα μας πει και αυτός. Ο Σιμών έχει προπτυχικές σπουδές από το Πανεπιστήμιο του Woods στην Πολωνία και έπειτα έχει κάνει διδακτορικό στο University of Sheffield, όπου και τον γνώρισα όταν ήμουν εκεί, όταν εργαζόμουν ως μεταδιδακτορικός ερευνητής, και πλέον εργάζεται ως Marie Curie Fellow, Experienced Researcher, στο Εργαστήριο Τεχνολογίας και Κατασκευών Οπλισμένου Σκυροδέματος, όπου ασχολείται με ένα θέμα όχι τόσο σχετικό με αυτό που θα μας παρουσιάσει, αλλά στο μέλλον θα έχουμε την ευκαιρία να μας πει και για το project που ασχολείται τώρα. Οπότε, Simon, the stage is yours. Vanessa, it was ready. Okay, I'll do it now. Okay.
Okay.
Maybe I turn off the lights.
Okay, yeah, we can turn on the front light maybe. Okay, thanks, that's perfect.
Yeah.
Okay. Good morning, everyone. Kalimera. Thank you very much for giving me this opportunity to give this talk on the front of you. It's been a while since last time I was looking into FRPs, fiber reinforced polymers. This is my topic that I was studying when I was doing my PhD, so it's about time. It's been a few years already, so it's about time to refresh my memory and look at this topic again. Just very shortly, my background, Lambros already covered it a bit. Just to make you sure that I'm not talking complete nonsense to you. This is a little bit of justification that I'm not doing research from yesterday. I have already around 10 years of research experience in dealing with advanced composites for construction. I'm from Poland, Łódź, where I was studying also and did my master degree there. I also spent around 2 years there working with fiber reinforced polymers as external reinforcement. Then I moved to the UK, where I was studying internal FRP reinforcement as reinforcement for concrete structures. Then I spent some time in London when I transitioned from reinforced concrete to masonry structures and earthquake engineering. And this is also where my idea originated to contact Professor Kutas and apply together for the Marie Curie, which I'm currently running since last year at the University of Thessaly. So that's it from the background, and let's move to the core of the presentation. I will start with a little bit sad information. I'm sure that most of you are familiar with this terrible accident that happened in Genoa in Italy with the Morandi Bridge in 2018. This catastrophe took life of 43 people and left around 16 people injured. The reason of this looks like it's a corrosion of the tendons, steel tendons in the bridge, which unfortunately gives an indication that some of the structures, also big bridges which have been constructed after the war, have already surpassed their design lifespan, and their internal reinforcement, as well as you see, pre-stressing tendons might have been compromised due to the aging and environmental conditions. So this is a message really to our generations of engineers and the future generations, that this is the problem that sooner or later will start coming out, and we will see this, hopefully, not this catastrophic consequences, but this is an indication that we need to strengthen the existing reinforced concrete structures sooner or later, or build the new structures using materials which have higher durability and longevity, which allows for more durable design. And this is where FRP composites come into play. What are exactly fiber reinforced polymers? There are some, I have some samples here that I will circulate now, which actually imitate the fiber reinforced polymers, or you can pass them around. You see, they are similar to reinforcement that we are using in the conventional reinforcement structure. They are in form of bars, in form of laminates, made of different fibers embedded in matrix, as well as shear links, which are used for as shearing process. You can calculate it, circulate it for everyone.
You can show them at the camera.
Okay. And this is something for the online audience. So these are the FRP, glass FRP bars that we are using as reinforcement. Of course, this is just a small sample, a very short one. These are GFRP, so glass fiber reinforced shear links that we can use as a shear reinforcement. These are some different GFRP bars that can also be used as internal reinforcement. As you see, they have different structure because of the different processing of the bar, which allows for better bond. We can use also some rowings of fibers, which we can later impregnate with resin. But I will explain this in detail a little bit later on. So as you see, there are different materials with different properties, and these materials can be used to strengthen or as a new reinforcement. I will circulate it to everyone so you can see it.
Maybe towards the end.
But let's make clear here one thing. I'm not saying here that FRP reinforcement can fully substitute regular steel reinforcement. Not as for now, because steel is a fantastic material, and it still allows for very, very safe design. Although we need to look in the future and really come out with some smart solutions which allow us to design structures more sustainably. So, what are the FRPs? You can see them really basically in every day. They're actually a legacy of space industry, which was very active in 60s, then moved to transport, aviation, and even sport equipment. Wherever we need lightweight, durable, flexible materials, we can use composites. The fiber reinforced polymers, this is how they call them. Composites are made of 3 essential parts, mostly 2 with some additives optionally. They contain fibers. They can be glass, carbon, basalt, and aramid. As you see, they have different colors on the samples that I showed you. Glass and aramid fibers are kind of yellowish. Basalt and carbon fibers are darker, usually black. The fibers are responsible to carry the loads, where the polymer matrices are responsible to provide a composite action between the fibers, as well as to give a final shape of the composite. We can also add some additives optionally, like plasticizers, bonding, and chemical agents, which allow for the matrix to achieve better properties. So as such, we can see FRP profiles in forms of profiles like you see, like hollow sections or closed sections, open sections, as well as laminates or bars if we want to use them as internal reinforcements. Now here we have some possible use of the laminates, as you see on the top photo, where we can glue the laminates directly to the concrete surface and strengthen the deteriorated reinforced concrete structures. But we can also use it as internal FRP reinforcement and make structures fully reinforced with FRP composites, which highly increases the durability of the structures. Now, the size of the photos is also intentional. Right now, the biggest application of composites is in strengthening of existing structures. The market for new structures fully reinforced with internal reinforcements, it's growing now, but it's still smaller than the market for strengthening. One of the reasons for that is that we really don't understand how to design safely large FRP reinforced concrete structures. We know we have adopted some of the provisions from the codes for steel, but to some extent, researchers are still and practitioners are still a little bit hesitant for that. But this market grows, and even I can tell you that recently I had a meeting in one of the technical committees of FIB, which deal with this FRPs in the field of strengthening as well as internal reinforcement. And some of the experts from United States have clearly indicated that the market for internal reinforcement is increasing now. And even recently, for every 10 projects with FRPs, 7 or 8 out of 10 was actually with internal reinforcement. So we can see that this market is growing, and it can even grow more in the next decades. So these are some typical properties for FRP composites. As you see, we have different fibers, different fiber types, and different properties can be observed. As you see, the variability in the tensile strength and the Young modulus is quite high. We can get something from 2,700 MPa in terms of tensile strength up to even 4,000. So if you remember how much structural steel can take, you can see that you can achieve tensile strength even up to 7-8 times that of structural steel. The same with modulus. We can go much higher even with the modulus, although this is only for some limited applications using carbon fibers, which are very, very expensive. And right now, it doesn't really make sense to use such expensive materials. So we rather focus on the use of glass and basalt fibers, which are quite good, let's say, deal in terms of stiffness of the reinforcement to price. So what's the difference between steel reinforced concrete and FRP reinforced concrete? So the main difference is that the stress strain behavior of the fibers is linear up to failure. So we can see that there is we don't have this nice yielding plateau that we can observe in steel reinforced concrete structures, which, as you will see later, is kind of complicated because we need to find a limitation for that reinforcement, which will allow us to safely design such reinforced structures. So if we take a fully reinforced glass FRP reinforced concrete beam, what are the differences? Basically, because glass fiber reinforced glass FRPs have lower flexure, lower stiffness of the bars, we will observe lower flexural stiffness, larger strains, larger deflections in the beams, wider crack openings, as well as less concrete will be engaged in the compression. So actually, you will see that all these mechanisms which contribute to the shear in concrete are kind of smaller. The contribution is smaller. So, and also because the fibers are only placed in one direction, the direction in the transverse stiffness of the bars will be also much lower. So as we see that this actually would result in situation like this. If we would test two identical beams, identical geometry, and put the same amount of reinforcement. One would be steel, one would be glass reinforcement, let's say, because the glass has lower modulus of velocity. We will see that FRP reinforced concrete beam will be more deformed, more cracked, it will exhibit more brittle behavior and lower load capacity. So now you might tell me, okay, so what's so special in this FRPs if they yield smaller capacity than regular steel? Well, as I said, I'm not trying to convince you that this is a cutting-edge technology and we should stop using steel and start using FRPs. I'm not any sort of FRP crusader who will go around and start selling FRPs. I'm just telling you that this is kind of something for something. That this is a choice that we make to construct new structures with materials which can live longer because of the non-corrosive behavior of this reinforcement. This reinforcement does not corrode, so we can technically design the structures for much longer than it would be in case of steel. The pros of FRPs is as you saw, high tensile strength, high deformability, non-corrosive characteristic, as well is a lightweight material. So it's easy to ship to the construction site as well as handle on the construction site, which provides you an opportunity to cut some costs in that. However, usually we are forced, because of the price of FRPs, carbon fiber reinforced polymers, we are forced to use lower stiffness bars. So we actually end up in stacking up more FRP reinforcement in the sections to achieve the same capacity. Another thing is the poor transverse stiffness, which kind of limits us to use FRPs only in one direction, and they have poor performance as dowels, whereas steel can do very well in any direction because it's an isotropic material. The most important for me is that it has no yielding plateau. So it kind of really changes all the concept of design. Although, as for now, we are really using the same concept as we are using for steel. But I will show you a little bit more later, and you will realize that there is a scope for some improvements there as well. So let's move to design philosophy for shear. I will start from this video just to show you how brutal a shear can be. Kind of I'm sure most are familiar with if structures are under design and fail for prior flexure failure. This is one of the beams that I tested in Sheffield actually. It has depth around 400 maybe 400 millimeters. No shear reinforcement at all, only done. There is some reinforcement here just to make sure that it fails here. So, as you see, this is some kind of failure that you really don't want to see at any ultimate limit state, because this is just catastrophic. So what we really do in steel reinforced concrete, if you know Eurocoat a little bit, you know that Eurocoat is so scared of shear, or it wants to be so conservative that it doesn't even take into account the contribution of concrete. Although the overall shear resistance comes from contribution of concrete and contribution of shear reinforcement. In Eurocoat, once the shear reinforcement is provided, we don't even care about the concrete anymore. We just take that. We basically make it a very conservative design. Because you saw that all these mechanisms in FRP reinforced elements are deteriorated because FRPs are more brittle, and all these mechanisms have smaller significance in terms of overall shear strength. We are not allowed to be, we don't have this ability to be so conservative in FRP design, really, and we need to take VC and VS, because otherwise we would end up with a very small contribution, and it would not make really sense to use these materials. So how do we deal with this? What do we do when we design FRP reinforced concrete elements? Well, this question arose at the beginning of 90s when we started looking at this. And really the most reasonable way would be to just limit the strains in the reinforcements, FRP reinforcements, bond longitudinal and shear reinforcement to the same limits that we limit it in steel. As you know, steel yields at around 0.2 to 0.25%. So the first idea was to, okay, let's do the same. Let's just assume that we are forcing our beam to the same strain, and then the same mechanism should be mobilized. After a while, we realized that we can actually push it a bit farther, and still nothing bad happens. So we can even go to 0.45%, and it was claimed that this is a safe design, nothing can go wrong with this. And this is to some extent true, but I will show you that what I found in my research, that actually this is not really a conservative approach, and at some cases for larger elements we can have some issues with this. So what we do really is the strain approach. As I say, we really say that strain in FRPs is the same as strain in steel, and the forces to be developed are also the same. So as such, we end up with the equivalent area of the reinforcement that we need to provide. And if you remember Eurocode equation for calculation of contribution of VC, it looks like this. We basically calculate a new area of the reinforcement, and this is how we really account for contribution of concrete in FRP reinforced concrete elements. There's a kind of very simplified approach that is directly adopted from the Eurocode. This is the Eurocode modification, by the way. Every country, every different continent has their own codes, and they also put their own modifications. We're not gonna go that deep here. We'll just focus on Eurocode because we are all familiar with this code. And yeah, and this is another just analytical explanation how they will deal with this. If we want to increase the contribution up to 45, then of course we need to apply a factor which will account for that. So this is for VC. How do we deal with VF, which is the contribution of the shear reinforcement? Well, since we are operating with the stresses here, it's pretty easy. We can just put those limits that we are interested in directly into the equation for truss analogy, and we can basically calculate the contribution of the shear reinforcement in this way. So as for now, I don't know, maybe it has changed in the last few years, but 4 years ago, the limit for the contribution of the shear links, so these square links that I circulated with you in the design, was from 0.25% to 0.5%. This is the maximum that we can do, depending. Canadians are less conservative, and they allow for higher utilization. Japanese code, if I remember correct, and British code was more conservative. Of course, we have to remember also that there is one issue with the FRP shear links. As I said, the transverse stiffness is much lower than the longitudinal stiffness along the fibers. So there is a risk of a premature failure in the corners adjacent to the longitudinal reinforcement. So we need to also account for that and reduce this stress to allowable stress in the shear links using this equation. So what else is important in shear? This is something that I was studying, and it's really quite complicated topic. It has been identified in 60s already, but I believe this is one of the reasons why we still hesitate with using FRP reinforcement for large reinforced concrete structures, because we really don't understand how this really works. Size effect in shear in reinforced concrete. What does it mean? It means that somebody observed a long time ago that if we design and test few identical beams where the only variable parameter is effective depth, we actually will observe lower shear strength at failure in the larger elements. And this is more pronounced for elements with A over D around 2.5, so shear critical. Once the element goes more slender and resists shear and loads more through bending than shear, then this effect is less significant. This is a problem, because if we are using the same equation without this reduction factor, we will end up predicting continuous, well, the same shear stress level across the span of the depth, and this will end up having large reinforced concrete members grossly under design, and this is something that can cause a failure of the structure. And actually, there was one failure of shear failure of a warehouse. I don't remember when was exactly that, but it was related to size effect. And since then, we started looking into this in more details. So, as I said, FRP reinforced structures are more brittle, wider cracks, more brittle behavior, larger deformations, a larger level of damage. So we can really expect that this will be much more significant in terms of FRPs. The definition of the cause of size effect is not, there's no consensus about this really in the literature, but it's mostly related to the degradations of the shear resisting mechanisms. So larger beams have larger cracks, and there is more degradation in this small resisting mechanism. For example, along the shear crack, the friction is smaller because the cracks are bigger. These are very detailed informations, and we don't really care about this in the design. We just apply some reduction factors, which you can see can tell you how little we know really about the size effect. As you can see, every code has different factors that are all over the place. Some of them give bigger reduction in the shear strength. Some of them, they give larger reduction. These are actually all the reduction factors that are applied in FRP codes for internal reinforcement, but they're really directly applied from steel reinforced concrete design codes, which I don't think it's correct, and I think many people have started thinking now that this is something that could be improved. So in my research, I was really looking into these two topics. One was size effect in FRP reinforced concrete elements, and the second was the relative contributions of VC and VF, so contribution of concrete and shear reinforcement to the overall strength of the beams. So if you see here, we have a collection of two large data sets of probably all beams that have been ever tested in shear. There is a famous database by Reineck et al. And the guys really collected everything that has been done since the 70s. Huge paper with I don't know how many pages really, but it's the most accurate data which many researchers work on. And really, when I compared this to my database that I collected for FRP reinforced concrete elements, which is of course much smaller, I started seeing some indications that actually it makes sense to argue that these reduction factors from directly adapted from reinforced concrete design codes might not be correct, because it's kind of looks more pronounced. And when I check the performance of some of the code equations for FRP reinforced concrete elements and plotted experimental results against the predictions, in ideal world, we wanted to see them really along this line where we see 1. Of course, shear has a lot of variability, so we really don't see it here. But what I didn't like is that this provisions for size effect really, they produce unsafe results for. Here we have effective depth of the element. So you see, of course, there is not many tests done on very big elements, but we see that the codes that we use in Europe and North America, except ACI, can provide some negative results. So I designed and carried out a series of tests on the beams when I was looking at different size of the elements with beams with and without shear reinforcement. And I was focusing really on size effect here and on the contribution of the FRP reinforcement. Now, we were lucky to be able to use the digital image correlation for this, but this is kind of a measuring tool which allows you to obtain full field information on every surface really that you are investigating. So we can see, really measure this displacement of any point on the beam. Now, of course, I was dealing with internal reinforcement, which you cannot do it using the AC because the internal reinforcement is from the definition inside. So we had to do a little trick here and use externally bonded, fully wrapped FRP links, which one might argue that are not really internal reinforcement. But if you know shear, you know that the performance of this type of reinforcement is strength dependent, not bond dependent really, and they essentially work similar to internal reinforcement. So really we adapted this way, and what we could do is to have a better insights in the strain and the utilization of the links. As you see, these dark spots are also strain gauges that I put, but the problem with strain gauges is that they give you very local information about the utilization of the material that they are put on. If the crack goes a little bit up, they might show you nothing really sometimes. So anyways, we had both strain gauges and DAC, and we were monitoring the utilization of the links in this way. I want to show you. This is a test on FRP glass, FRP reinforced beam. Actually, Lambros, I think you were there in Sheffield actually when we were testing. I think so. So we see pattern failing, one by one link fails, and you can see that it's quite brittle. And what I was doing, I was repairing the one side and testing the other span of the beam, which can really provide you two specimens from one if you do it properly. And actually, I got quite good results from this. There was another video. Just show you. This one is carbon shillings. These carbon shillings are they are stronger, let's say that. So we can expect a larger break. So you cannot say that FRP reinforced concrete structures are not brittle after these videos, I suppose. These are some cracking patterns from the tests, but what was very interesting that we observed is that actually the initiation of the crack, the initiation of the shear crack always starts from the tip of the flexure crack, and then it goes up to the compression zone, and when it cannot go further, goes backwards and propagates along the horizontal reinforcement. But what was interesting, what I found there, is that actually this initiation point it's actually a function of the overall or effective depth of the element. And the higher the element, the taller the element, this initiation point was actually placed lower, which really affected the inclination of that shear crack. And these are some test results. These are results from the longitudinal reinforcement, strain in the longitudinal reinforcement. And this is the first indication that I realized that something is not really according to the literature that I was studying. So you see that I said before that up to 0.45% or 4,500 microstrains, if you will, actually nothing should happen to the beams. But the tallest beams, which are not really that frequently tested in the labs, actually showed me that you can get a little bit below that 4,500. And if you test even larger, what I found out later, you can get even lower strains. So actually, that gave me already an indication that there is something not consistent with the current state of the art at that time I was studying. Here are some results from a size effect. The experimental results from the beams are gray. Here we have no shear reinforcement. Here we have shear reinforcement. If you look at this, you can see that there is a kind of size effect that for small beams, which were the smallest were around 240 millimeters, tallest were around 460. You see that kind of it decreases if you take, of course, average of all these tests. They were the same tests. You can kind of see this decreasing trend. If you provide shear reinforcement, according to the literature too, you should not see size effect because it's effectively mitigated. And I saw that too. So this is something that we did using the DAC, and this was really helpful because this really allowed me to really accurately estimate the utilization of the shear links. So this is the other side of the beam that you didn't see on the movie. It's covered with a speckle pattern, which makes it very which allows us to monitor really the displacement between these speckles. And you can really see how much utilization of the links we achieved. What I did later is I took all the beams and I calculated the utilization of these links only based on the active bond length, the length that was really activated. This is really the most accurate way how to estimate how much job those shearing links did. And then what I did is I calculated the shear force produced in every of the links and subtracted it from the total. So at the end, I had contribution of the shear reinforcement, which was basically this, and everything else was contribution of the concrete. This point is the shear cracking. So this is where the shear crack starts, and this is what we got as a contribution of concrete. This is something that, of course, you don't see in the codes of practice because they assume that the contribution after shear cracking is constant. We don't see this degradation. But the very interesting stuff was that when I compared this across the different sections, I saw that the larger the section, actually, the less concrete contribution, which makes sense because we have larger cracks in larger elements, and we kind of force the shear links to work harder. So although size effects should not really exist in elements with shear reinforcement, you can see that the size related phenomenon are clearly present here, which was very interesting actually. And here, what we have is the contribution of the concrete, experimental contribution of concrete against the longitudinal strain. And this also was very interesting to see that actually when we increase the size of the decrease in the longitudinal reinforcement is steeper, and this made me think that why not reflect back on these design equations from late 90s and try to improve them a little bit and this to account for this effect. So here we have a set of data where red triangles are my data from my PhD. I dug a little bit deeper and also found some other research studies where people were testing larger elements, and then excluded all the elements which were too slender or too much as like corbels, and I really saw a quite clear trend that maximum strain in the longitudinal reinforcement should not be really fixed value, but it's really a function of effective depth of the beam. And when I worked on it a little bit, it kind of showed that it can be easily applied as a reduction factor, additional reduction factor to already existing reduction factor for steel reinforcement. And this can help to fix those problems that I showed you at the beginning. So basically what I did is from the one on the top is that was already in the literature, was placed in FIB Bulletin 40 as a provision for VC, for the contribution of concrete. I made it a little bit more pronounced, so to get all these guys, which we see here, a little bit up. So you see that applying that provision really helped to give those predictions a bit more accurately. Now you might say that, okay, all this work for only shifting up few data points up. Yeah, that's maybe true, but we don't really have that much data. It's not easy to go to the lab and test beam which has 800 millimeter size. It's kind of a lot of work. But the most interesting thing that I found in my research really is that I used the same equation for steel reinforced database. And what I observed for some reason is that it can be directly applied to this steel reinforced concrete structures. And as you see, can reduce the coefficient of variance up to as much as 25% actually. This is a really huge improvement to the existing code, because if this is the performance of the existing Eurocode equation, which should make really that set of data points along the line, it clearly doesn't. You can see the same size effect that I was showing you at the beginning of this presentation. If you use the equations that we developed at the University of Sheffield, you can really bring this a little bit down and make this design more economic and robust. Okay, how much time do we have? 10 minutes left. I will skip this another model that I did here. It's just for the shear reinforcement. It's more a fun fact than a really model. There's obviously not enough data to support this. But I think where to go further with this topic is really to start looking into real contribution of the concrete. As we saw that the contribution of concrete after cracking decreases and the contribution of the shear reinforcement increases. What we do really now is level 1 approximation, that we take constant contribution after cracking and contribution constant contribution of concrete after cracking and contribution of reinforcement, which is also constant based on a fixed angle of 45 degrees. Does this produce an unsafe design? Not really. It's for some reason pretty accurate. It's not very accurate, but it's conservative and reasonably accurate. But we really don't predict what we are claiming that we do. We don't. The VC that we are not calculating is not really the real VC, and the VF or contribution of shear links is not really that one. To be more accurate, we should go towards level 2, where actually I didn't discuss it because I skipped that, but actually the most accurate would be to really operate with the variable truss angle and really reduce the contribution of concrete failure accurately to get very robust and economic design in FRP reinforced concrete structures. This is just another graphical explanation of the situation, which I can skip now. And basically, this is that's it that I wanted to cover today. I hope I didn't bore you too much with this presentation. If you're interested in experimental mechanics and testing concrete and masonry structures, please follow our Instagram at contest UTH, where you can get the latest news from the world of science. And that would be all. If there are any questions, I'm more than happy to answer them. Thank you very much.
May I start?
Yeah.
Let's see if there's any questions on that.
Could you please move the slide where you showed us?
Θες να παρακολουθείτε, δεν ακούγεται καθόλου.
Which slide?
Okay. Could you please? Yeah, this slide. You
Yeah.
told us on the right side where you have the steel reinforced concrete
Yes.
beams that the current design formulation gives a little, a coefficient of variation higher than what you fixed down.
Lower.
I mean, this is all the current formulation on the top.
At the top is the current formulation.
And this is higher coefficient of variation compared to what you propose, let's say.
Yes.
But on the other hand, on the top, the current formulation gives predictions on the safe side.
Yes.
Because V experimental is higher than the predicted, so the predicted values are on the safe side. What about the one that you propose that has some values?
Okay, that's a very good question. Thanks for covering this. Well, as I said, this was something that we found at the very last moments, really, and I was not. Although this looks the most interesting from the whole work that I've done, I didn't really go deeper into this. But when we produce analytical equations, we don't really care that much about the average values, really, because fixing this is a matter of applying a small factor on the front of the equation and everything goes up. Yeah, this is just the verification of the equation that is currently in the Eurocode. If you want to make it safe, you can do it in 5 seconds. Just bringing it up. The key is really to have consistency in the predictions of the code equation, which you can see. Of course, it's still there is a cloud of data here, but it's much better than here. Of course, this should be, if you want to use this equation, you should really calibrate it in a way that it gives a safe range of results. So they are always on the green field.
Thanks. Any questions?
Yeah.
Regarding the question of the truss, the integration in the Eurocode is not in the safe factor.
Of course not. Of course not.
Can you repeat the question?
The question was if we used any safety factors when we were checking the experimental data against the predictions. Of course, when we do this sort of comparisons, we never use any safety or material factors to be as close to the predictions as it gets. So yes, it was without any safety factors.
You have the question on YouTube. Just give me a minute to go and check it.
From
YouTube.
I was on YouTube.
We are popular. I don't see.
Are there any questions from Teams, from MS Teams? Would you like to raise your hand? Θέλετε να σηκώσετε το χέρι, υπάρχει καμία ερώτηση? Όχι, δεν υπάρχουν ερωτήσεις από εδώ. Εντάξει, ευχαριστούμε. Θα υπάρχει μια ερώτηση ακόμα από το YouTube, θα την απαντήσουμε.
Μέσω του κινητού δεν μπορώ να τη βρω την ερώτηση, οπότε θέλουμε εσύ τώρα δεν θέλω να κάνω.
What is the benefit of using a material which is not as ductile as steel? We're talking about brittle material, right?
Well, we don't know, but
So we're talking about internal reinforcement.
yes.
For reinforced concrete, when you use steel, the main benefit of using steel is the ductility. Right?
Yes,
And we are introducing now a brittle material to work together with another brittle material to produce a.
As I said, I'm not trying to say here that this is the next direction of the research. the biggest benefit of FRPs is inside the concrete is definitely the anti-corrosive properties that we can achieve. So we can design not like Eurocode says for 50 or 100 years, but we can go for, I don't know, maybe 500 years or 1,000 years. Why not? If it's well maintained. And you know, this is a field which has been started. No, it's not a new field, but it has been progressing quite slowly when I started working on it, and even a bit earlier. And I see now that the pace of this is increasing. So it's a matter of really more research on this and improving maybe even the ductility of these fibers to be able to introduce this into the market at faster uptake. So,
have you seen, because I haven't done any research on that yet, but I remember when I was back in the States, they used to have, they used to experiment on bars, make not just from carbon, but they will combine carbon and glass.
You can optimize in this way. You can do it with steel together and reduce a bit of. Or you can do it in, for example, you can have a section with steel reinforcement which has more cover, and then put outside the FRP reinforcement, and this way you will increase the durability.
But these hybrid systems are not.
Which systems?
Any hybrid system, like with two
they have been research done on this for sure, but
I know in research wise,
I'm not familiar in any developed systems. Yeah, I'm not familiar really. In any systems. I think the next really step for internal FRP reinforcement is really making it more durable, really, and less.
As far as I know, the biggest problem in fabricating these messes, because with steel you can bend it. If it comes a little bit short, you can bend it here. You cannot do anything like that.
You can actually bend it. You can bend some of the FRPs, but you need to hit them up to do this. And this also causes a reduction of the strength in that point. So the problem is also with the shapes. Really, to achieve the shape, you can't do it on the side.
Precast factory, the precast factory probably would be relatively easy.
For sure, this shear links has been done like this. If you see, not sure how. Do you remember how they did it? How this shear links
around the timber beam, I think.
Yeah, and then
they wrapped around the timber beam, so and then they cut it in pieces.
Yeah.
This is just continuous fabric. I will add on the question of Professor Konstantinou, and I will ask you this. In Greece, because we have earthquakes, we want medium or high ductility class of buildings, which means in the regions where you expect to have large plastic deformations, in the formation of plastic hinges, you should normally have a large capacity of plastic deformations. From what I understand, you cannot use
no ductility there, but if you join this with some confinement using FRPs, or maybe some rubberized concrete, maybe not rubberized concrete, but if you use it together with some other benefits of FRPs, then you can possibly get some ductility.
What about in slabs, reinforced concrete slabs? Because you have a large amount of reinforcement in slabs, and you don't care really about ductility because it mainly holds, the transversal loads. What is the benefit?
But I can tell you that I've seen a lot of applications for FRP bars in shallow decks, really, in shallow reinforced concrete decks. So this definitely is one of the applications for this, and it might be even cost efficient in this way. I really can't give you exact numbers because the prices also change on the market. It really depends. It really depends on
For sure,
on the problem
the cost of maintenance will be minimized.
Exactly. So long term, really, if you want to look at the cost long term, then you might end up using even maybe carbon FRP reinforcement rather than steel reinforcement.
Okay. I have a question from YouTube. It says, what design code do you use for the design of FRP cross-section in slide 13?
What?
In slide 13, what design code do we use for the design of FRP cross-section? I don't know.
But slide 13?
Slide 13 of the presentation.
Slide 13. I don't remember, to be honest.
Okay, it's an honest.
This is from some research of my colleagues. Most probably it was the Eurocode equation modified to calculate. But slide 13, there is no calculations here.
Yeah, I don't know. Maybe
this is just data that is
maybe
plotted.
there is a misconception. Yeah, this purely
In general, okay, I can tell you what kind of codes you can use for design in shear. You can use British code here, BSA 99, Japanese code, very conservative, not really useful now. This is Canadian code, quite okay. This is Canadian.
It's Italian.
This one is Italian. Yeah. I said Canadian, sorry, Italian. This is Canadian as well as this one. They allow you to use the variable truss angle, which is very interesting. However, they're also not very accurate. I found the most accurate is this one and FIB bulletin. These are really.
So, any questions? Κάτι στα ελληνικά, ό,τι θέλετε και το μεταφράσω. Ήταν όλα καθαρά, ξεκάθαρα. Εντάξει. Carlos, we don't have any other questions, so.
Okay. Thank you again for giving me this opportunity. It was very nice to presenting you this material. If you have any other questions later on, maybe just please leave.
Are there other applications of this product or just for making it reinforced?
Are there any other applications than reinforced concrete? Yes, you can use it in timber as well. You can use it in even steel structures as external strengthening. Masonry a lot nowadays, but not really FRPs masonry. FRPs are not really good for masonry because they detach very quickly. They are not really compatible with masonry. So we.
If we make like a pipe by FRP,
yeah.
So it's thinner and solid. What about the strength then?
If we make a pipe made of FRP.
Yes, made of FRP, so use it in underwater transportation of gas maybe. So we will
Replacing steel pipes with FRPs, let's say.
No, complete FRP pipe. Can it absorb the tension, water tension, or if we...
Under pressure, you mean?
Yes. It's not strength enough. It's not strong enough.
You mean if we have a pipe, for example, and the pipe is subjected to loads transversely this way?
No, I think the pressure from what is inside, gas or whatever. Liquids in pressure.
Okay, so if...
It was
I think I know what you mean. I mean,
corrosion was affected.
Well, if it's FRP pipe, you mean?
Yeah.
If it's an FRP pipe, then you don't have corrosion issues because they don't corrode.
Can we make a pipe made with FRP so we don't care about corrosion? Or it's not strong enough? Okay.
It can be. You can use FRPs to make pipes. It's a matter of design really, and the orientation of the fibers. Maybe you need to put them in hoop direction instead of in longitudinal direction. But definitely there are applications for this, for the pipes, as they are quite durable.
Nice. Okay, so let's bring this session to the end. Thank you, Szymon.
Thank you, guys.
Thanks, everybody. Κωστής με Ιντερνετ, μπορεί να το διακόψω. Κωστής να το διακόψω.